Good day, everyone. This lecture is recorded for our lecture sessions this week from August 8 to 12, 2022. Okay, last time I've shown you a factorial program to do factorial computation with output in the IAS. Now, the next thing to do is to create a program that will do factorial computation using a loop. And I have introduced you the instruction set of the IAS, and I pointed out that there's an equivalent, no? There's a close equivalent of the CB command. The CB command is our main command in the analytical engine that we use for looping. CB is a jump, will jump if the last result is negative. Now in the IAS we have a jump plus, which will jump forward or backward depending on the last value, if it's positive or non-negative. So they're almost the same, but they're not exactly the same. And substituting jump plus with CB is erroneous because CB is actually a jump minus. What we need is a jump minus. Unfortunately, we don't have a jump minus in the IAS. Okay, and then later I will explain your assignment. To make a long story short, let us translate the fourth factorial with loop from the IAS. It's here now. One of the main problems we have here is we need to change the addressing, because the addressing in the IAS starts with 1 because the first command is a jump. Okay, because it's followed by data. So in our IA analytical engine, we'll have to shift everything by 1. So the 100, the 00 will have a 0, and the 4, which is our first multiplier, will move it to variable 1. Okay, and then our subtrahend will move it to variable 2. The second variable will move to variable 3. Okay, and all our commands later will just transform to add by 1. So this is L001. This becomes L002. This becomes L001. This becomes S002. We're just moving the variables one address down because we need to accommodate for the 0. So this is 1. Nothing changes here, no? I hope you are convinced that the sequence will still be the same and the result will still be the same, just like changing variable names in programming languages. Okay. Then this will be L002. This will be L001. Okay, we're just changing. Don't need to trace that anymore. What we are going to do is to translate. This worksheet is available in our Daygler site as the IAS analytical engine and IAS conversion of the fourth factorial program. Okay, please find it there. I think it's here. Let me show you where it is. This one. Okay, it's there. So anyway, let's translate the move. So unlike in the analytical engine, we multiply before we load. Here we load before we multiply. So the first parameter is m of 2. So we say load m of 2. You follow? And then we multiply it with mul of 1. This is, by the way, 4L. Then in 4R, we mul m of 1. You follow? And then we store 5R. We store m of 2. So in this case, now the accumulator, this is F, this is 4, this is a jump, 4, 0 to 19. Okay, this is a 4, this is a 1, this is a 1. So this is a 4, 1, 1. So here, the accumulator here is load M of 2 is 1. Mul M of 1, which is 4, this becomes 4. Store M of 2, this becomes 4. Okay, this is our partial product. Okay, and then we do a minus here. We'll just skip so we can show the equivalent. This is 5L, 5R, 5L pala ito. This is 5L. The next is 5R. Okay, we do a minus. So we do a load first, load M of 1. Okay, and then in 6L. Okay, we do a sum M of 3. Okay. So load of M of 1 is 4. Okay. Sum M of 3 is 1, which this becomes 3. And then we store 6R. We store S of 1. M of 1. Because it's S001. Okay. So now this is M of 1, this now becomes 3, which is our next multiplier. We do a minus again, okay, to compute, to prepare us for the loop. No? Then we'll do have this is 7L. Okay, so we load first, load M of 3. In 7R, okay, we sub M of 1. Okay, we sub M of 1. So if you load M of 3 here, this becomes 1. Okay, minus 3, this becomes negative 2. Now the problem here is we don't have a CB, because a CB is a jump minus 8L. Okay, so what if we have our 8R here? This is a trick that can be done, no? To substitute the jump minus with a jump plus. Okay, that's because we don't have a direct equivalent. What we'll do is we'll do our jump to the here. This, I think this is the, where's the low here, no, 4L. We'll do our jump to 4L here, no? Do you follow? And in 9L, we'll proceed with the lot, with the load of M2. Okay, and in 9R, we will proceed with mole of M1. And then in 10L, we'll proceed with a jump to 10L. Okay, this is our halt. Okay, so what will we do with our jump plus here? We'll just say jump plus jump plus to 9L. I hope you follow, no? You get this. 9L. So which means that if the last result is positive, we'll jump to 9L, which will proceed to halt, which will load M2, multiply with M1, and jump back to and proceed to a halt. Now, if it's negative, it will just proceed to 8R, and 8R will send it back to the top of the loop. Do you follow? I will not trace this anymore, but you see that the sequence is followed. Okay? Do you follow? And this will work. However, the main problem with this is called the spaghetti code. Okay? Because we are trying to intertwine the sequence of our code in the sense that we are jumping forward one line, and the line in between will jump backward a few lines before. Okay, so this is a spaghetti code. Now, if you keep practicing writing code like this, you will end up writing very complex code. Okay, so shortly, I will introduce you the looping techniques that will help you make your loop structures better and avoid spaghetti code. Okay, you can use these concepts also in your other programming courses. Okay, you can download this as looping concepts in our Daigler site. What is a loop in programming? A loop is a repetition. No? It's a sequence of instructions that is repeated until a condition is reached. It's also called a repetition. Repetition control structures in programming languages define how loops are organized. There are two main organizations of loops. Before we go there, let us introduce the parts of a loop. Usually a loop has a head, which is the start, the first line that is repeated within a loop. Then it has a body, the set of commands with the head and the tail that composes the repetition. The tail, which is the last command that is repeated within a loop. So in this factorial program in the analytical engine, we have the minus as the head and the CB print 11 or question mark 11 as the tail. Now there are two looping structures. No, you have in C# you have a while loop and a do while loop. A bottom up structure like the fourth factorial in the analytical engine is a structure where repetition goes from the bottom or the tail back to the head of the loop. You will distinguish this because the condition is at the bottom. No? When the condition is at the bottom, it's the bottom up structure. The top down loop is a looping structure which goes directly outside of the bottom after the tail, like this. No? Jump 9 to 19. This is outside of the loop already, based on a condition. Repetition is done without a condition at the bottom because the condition is at the top. Okay? If the condition is at the top, it's a top-down loop. Okay. So there are two types of conditions. No? Condition for termination, which terminates the loop when the condition is reached. And the condition for continuation, which repeats the loop when the condition is reached. No? Like repeat until and repeat while. While is a condition for continuation while. Until is a condition for termination. Okay. Now let me proceed by creating a top-down version of the fourth factorial program in the IAS. And you will see that it has no spaghetti code. Okay. Let me copy this. Okay. I cannot convert this line per line anymore, no, because they are not, they are different. Okay. So this is the same top-down loop, which you can see in our slide. Let me just trace this now. Okay. So this is the factorial program now. So the first is jump 4 to 19, which is here. And our head of the loop is here. After the condition, jump plus 9L if the condition is reached. And the bottom is here now, which go back to 5L. 5L is our head, not 4L, okay? 5L is our head. So if you have 4 here, this will become 4. This becomes 1. Okay. M3 will be set later. Let's start tracing this. Load negative of M1, so this becomes negative 4. Add M2, so this becomes 3. Negative 4 plus 1 becomes 3. And we store it to M3. This is, I think these are a partial product. Okay. Now, Jump plus. No. Add M2, this is -3, I'm sorry. No. Because -4 plus 1 is -3. I'm sorry here, -3. Okay. So jump plus 9 to 19, it will not do a jump plus because it's a -3. Okay. The load pass absolute M3. The absolute remarks, or rather operator, will remove the negative sign. Load absolute of M3, this will become 3. Mole of M1 is 4, so this becomes 12. Okay, and we store them. This is our partial product anyway. This is our next multiplier. Okay, 12. Okay, and then we load M of 3. M of 3 is -3. Okay, add M of 2, so this becomes 2. Okay, and we jump 5 to 19. So this one. Okay, so we'll copy this because this will be our loop, and we will store the last values. Okay, the last values are for the accumulator, it's 2. For M1, it's 12. Add M of 2, by the way. When we add M of 2, this becomes -2. Okay, not +2. So this becomes -2. Okay. It's 12. This is 1. This is -3. Okay. So the first pass, no? Second pass is store M3. So we have here the accumulator will be stored here as -2. Okay. Jump 9 to 19. It will not jump because it's a -2. Okay. We load absolute of 3, M3. So this becomes 2 because it's a -2. And then we mole of M1. M1 is 12, so this becomes 24. And we store to M1. So this is now our next partial product, which is 24. Okay. And then we load M of 3. M of 3 is -2. Okay. We add M of 2, so this becomes -1 because it's M of 2 is 1. And we jump 5 to 19. So this is now our third repetition. There's no condition, no? We just jump because the condition is at the top. Okay. The last values will be, this is -1. Okay. This is 24. And this is -2. The next command is store to M3. M3. So the accumulator is stored to M3. This becomes -1. Let's erase this. Okay. Then jump 9 to 19. It will not jump because it's a negative. So we load positive of M3. So this becomes 1. Okay. Mole of M1, 24. So this becomes 24. And store of M1 is 24. Okay. Load M3. So this is now -1. Okay. Add M2, which is 1. So this becomes 0. Okay. And jump 5 to 19. Okay. We'll jump 5 to 19. This is our last, maybe our last pass, no? Okay. Store M3. Our last values are 0, 24, and -1. Store M3, so this becomes 0. And jump plus 9 to 19. Now it's now a 0. So we will now have to jump to 9 to 19. We'll erase this. Okay. 9 to 19 is a halt. Okay. Do you follow? So this is now a halt. You get my point? So take note, we have a different sequence, no? Because programs sometimes cannot be the same. This is a top-down version. This is the first one is a bottom-up version, but we have a spaghetti code somewhere at the end. Okay, and you see that The top-down version, it's simpler, no? Because it doesn't have the extra spaghetti code. Okay, any questions? So you can download this worksheet from our Dagger site here, no? Fourth factorial loop conversion to IAS bottom up and top down. Okay, I hope I'm clear. Now, before we end, I'd like to explain the programming assignment for the IAS. I think it's up already. Yes, no? Due on August 15. Okay, what you do is to write a program that sums the first four numbers of the IAS without loop, no? And give a trace in the worksheet, saving it to sheet 1. Okay, you can use the same factorial program and convert it, no, to IAS. I think we've done that. Write a program to convert Celsius to Fahrenheit for the IAS and give a trace. We don't have to determine fevers or not. No? And then write a program to compute the average of the first three numbers for the IAS, this time with top-down loop. Okay, and give a trace in the worksheet 3 and pass this as an Excel sheet. Okay, I hope I'm clear. I'm going to answer questions, no, when I return back on August 15, 16. Any questions? Please post them, no, later. No. Thank you very much, and I hope you read this and view this so that it will help you solve our problem. Okay. Bye for now.